Good morning, colleagues. Welcome to the presentation on DC circuit breaker research in the promotion project. My name is Dragan Jovcic. I'm a professor at University of Aberdeeen. I'm also director of Aberdeeen HVDC Research Center. In the promotion project, I'm a work package 6 leader. DC circuit breaker is one of the key components in the DC transmission grids. They will have a significant impact on the DC grids in terms of cost, protection system performance, and transient response, DC grid reliability. The key remaining challenges with the circuit breaker development are reducing the opening time, reducing the cost, reducing energy absorption. In this presentation, three different aspects of the research on DC circuit development will be presented: disconnector opening voltage control, bidirectional DC circuit breaker with a single main valve, and the series LC DC circuit breaker. This slide presents the concept of controlling the voltage across the ultrafast disconnector. The main valve of the hybrid DC circuit breaker will be modular with the possibility of individual control of these modules. In conventional hybrid DC CB, all modules are inserted simultaneously when the ultrafast disconnector contacts are fully open. The proposal is now to gradually insert arresters one by one within the 2 millisecond period while UFD contacts are opening. The figure on the left shows the insertion of arresters one by one. All 8 arresters are inserted while the contacts are moving. The graphs in the middle show the simulation results on a 320 kilovolt 16 kiloampere DC circuit breaker model. The blue curves show the conventional circuit breaker and the red curves show the results of the proposed topology. In the lower graph, we can see that the peak current is reduced by approximately 30%. The graphs on the right show the parametric study of the peak fault current and energy dissipation depending on the inductance size. We can see that we have a significant reduction in peak current and energy dissipation. This slide shows the experimental verification of disconnector voltage control on 500 ampere 1.3 kilovolt prototype at University of Aberdeeen laboratory. We used 8 cells in the main valve, and our UFD has a 2 milliseconds opening time. Graphs on the left show the voltage and the current, and we can see that the proposed concept reduces the peak current by approximately 30%. The lower graph shows that the energy with the proposed concept is also reduced by approximately 30%. The graphs on the right show the control signals to each of the 8 individual cells, and the lower graph indicates that we can achieve voltage control in the first 2 milliseconds, and then there is a smooth transition to current control for the next 25 milliseconds. This slide shows the proposed hybrid bidirectional DC circuit breaker using a single high voltage valve. The figure on the left shows the conventional hybrid DC circuit breaker, which has 2 main valves. One is required for each current direction. The figure in the middle shows the first topology of the proposed concept. Here we have one high voltage valve, and there are additionally 2 double throw mechanical switches. The opening time of this concept is either 2 milliseconds or 4 milliseconds, depending on the original configuration of the switches. On the right-hand side, we can see verification of the concept on a 320 kilovolt 16 kiloampere PSCAD model. This slide shows the second proposed topology with bidirectional DC circuit breaker using a single high voltage valve. Here we have additionally 4 ultrafast disconnectors and 4 low voltage diodes. In this case, the opening time is 2 milliseconds, which is exactly the same as the original hybrid DC circuit breaker. On the right-hand side, we can see the verification of this concept on a 500 ampere 1.3 kilovolt prototype at Aberdeeen laboratory. This slide shows the experimental equipment for verifying this concept. The test circuit is rated for 900 volt with a peak current approximately 1 kiloampere, and there is a possibility of electronic PWM voltage control across circuit breaker. Hybrid DC circuit breaker has load commutation switch of 600 volt, 500 ampere. S1 is in-house made air disconnector with 2 milliseconds opening time and 2 millimeter contact separation distance. S3 and S4 are similar to S1, but they are developed as double throw switches. D1 to D4 are 600 volt 80 ampere diodes. Energy absorbers are EPCOS arresters. This slide shows the new concept of a series LC DC circuit breaker. The main idea here is to insert the capacitor in series with the DC fault current. The benefits of this approach is that the fault current will become AC and it will have zero average value. That means that the fault current can then be interrupted with any normal AC circuit breaker. Since it has a zero DC average value, potentially this fault current can be interrupted with zero energy dissipation. The peak AC voltage is expected to be 2 to 3 per unit, which is higher than approximately 1.5 per unit normally seen in hybrid DC circuit breaker. Therefore, we are trading higher voltage for less energy dissipation. We can see that the capacitor is in parallel with the main switch, which is the concept researched in many different circuit breaker topologies. The benefit of this approach is that the voltage gradient is now limited, and we have defined the voltage across the main switch. The commutation from the S1 to the capacitor can be achieved in many different ways, for example, using a disconnector with the contact overlap or with a separate commutation switch. This slide shows the experimental verification of a series LC DC circuit breaker. Here, switch S1 is air disconnector with 2 milliseconds opening time. S2 is a standard AC circuit breaker. The trip signal is sent at 0 seconds, and we can see that at approximately 500 microseconds, 130 ampere is instantaneously commutated from switch S1 to the capacitor. In the upper graph, we can see that the capacitor voltage is linearly increasing from 500 microseconds to 1.5 milliseconds. The graph on the right shows the measurements on the ultrafast disconnector. We can see that the contact position is increasing from 0 seconds. The separation distance, Z, is increasing from 500 microseconds. And we can see that the contacts have a velocity of approximately 2 meters per second. As the conclusion, we can say that the key challenges with the future DC circuit breaker development are reducing opening time, reducing costs, and reducing energy dissipation. 3 different research approaches on improving DC circuit breaker have been shown. Controlling disconnector opening voltage is shown to reduce the peak current and energy by approximately 30%. Bidirectional DC circuit breaker can be developed with a single HV valve, thus reducing the cost significantly. And it is also shown that the new proposed topology with series LC DC circuit breaker potentially introduces significant improvement in the opening speed and the lowering energy. Thank you very much for your attention, and we look forward to any questions.